There we go. So this is our last section on cryptography, which is a shame because I really enjoy cryptography. So yeah, we've just been covering, I believe it was digital signatures as well as key management, as well as a little bit on password hashing. So I just wanted to give a brief review on everything that, well, not everything, but what the were talking about before we dive in. So we talked about this scheme called RSA. It stands for Revist Shamir Alderman, which is just the last names of the inventors put together. It actually works as both an encryption scheme and a digital signature scheme. Really quickly, could I just ask, have either of you taken CS70 already?
I haven't. Um,
Okay. So if you have taken CS70, there's a little bit of review. And if you haven't, I'll try to do my best to go over really quickly just how it works. I can't get into too much of the specifics because that's an entire math thing on its own, but I can do my best. So yeah, and we for RSA in this class mainly we'll teach it for the purpose of digital signatures, just because we have El Gamal for encryption already. Here's how it works. I'm actually going to just skip over this slide and share my screen. Essentially, what we have, this pulled up. What we have, I'll just go to the bottom. What we have is this theorem is called Euler's theorem, and it essentially says if you have some number a and you raise it to the power of, this is the Greek letter phi. If you raise it to the power of phi, it's equivalent to 1 in a finite field mod n, and this is if a and n are co-prime. And so when we look at RSA, what we want, am I not sharing my screen? Oh, I didn't hit the button. Sorry about that. Okay, you should be able to see it now. We have this theorem. This is Euler's theorem here, which basically says if you have a number a and you raise it to the power of phi on n, it's equivalent to 1 mod n. And this is Euler's, I'll just put Euler's theorem here. You'll have to go look at CS70 in order to go over why this is the case. There's a lot of weird stuff with prime numbers. But essentially what we want is we want to be able to take some m, raise it to the power of e, and then when we later raise it to the power of d, we want to get back this m. And this is going to be over our finite field n. So we see here that immediately if we multiply this by a on both sides, you end up getting 5n plus 1 is equivalent to a mod n. So this looks pretty similar to what we want to achieve. So what we want really is for ED to be somehow, we want it to be equal to phi n plus 1. If we can find ED such that it's equal to that, then we have found two numbers that we can use for this RSA scheme. In fact, this could be any multiple of phi, just because going back up here, if you multiply 1 by itself an infinite number of times, you still get out 1. So what we really want is for ED to be some multiple of phi plus 1. Before I continue, the phi function is called Euler's tangent function. What that is out of scope for this, but essentially it's the number of co-prime numbers between n and 1 that are, no, between 1 and n minus 1 that are co-prime with n. Again, I won't get into too much specifics for that. But essentially what we can do is this is equivalent to just saying E times D is equivalent to 1 mod phi, which means E is the multiplicative inverse of D mod phi. And so if we just choose E to be some prime number, in class we chose E equals 3, then we can use CS70 stuff to get your D is the multiplicative inverse of E mod phi. And so that then when we go back and we plug in m to the ed equivalent to, well, m to the ed mod n, sorry, Then you have this ed is equivalent to k phi n plus 1 mod n, which, splitting that up using our properties of exponents, is k times 5n times m mod n. This just cancels out to 1, so this is equivalent back to m mod n. So I believe the professor went over this all in lecture, but I wanted to just cover it because I know it's a lot more math than we have been covering before. So does this all make sense? Are there any questions? Okay, I can't tell if that is yes, I have a question, or yes, this all makes sense. Okay, cool. Then I will, this is just the same as my slide. I just wanted to be able to write it out. So if you look back on my slides, you'll just see the same sort of number theoretical stuff. Oh yes, I forgot to mention, the public key ends up being the 3 from E as well as our N. And if everyone uses the same E, then you can just publish N because everyone knows that E is 3. And then your private key that you keep to yourself is D. Get the zoom back open on this window. All right. We've also been talking about key management. So just how can I, as some user of a service, know what Bob's public key is? So we went over two main constructs. We talked about this trusted directory. Essentially, there's some entity or organization out there that I just ask for in order to get keys. So if I want Bob's key, I'll just ask the trusted directory, hey, can I have Bob's key? I would, in order to have a secure communication with the trusted directory, I would already have his public key, its public key. And we talked about some drawbacks. Mainly, it's difficult to scale up. If you have one entity with every single public key for all people ever, it's kind of a single point of failure. And along those lines, it's a single point of failure for availability if the adversary just DOSes, denial of service, DOSes the trusted directory, then suddenly no one can get anyone's keys. And it's also a single point of failure for security because if the trusted directory's private key is compromised, then all bets are off. Security is completely compromised. So we came up with this other construct, or this other mechanism, I'll call it. It's just this certificate chains and hierarchies. And essentially, instead of a trusted directory, you'll have some trusted certificate authority. And that authority has the ability to sign certificates using its private keys. And this certificate, I'll just skip forward a slide, but this certificate will include a signature over the public key as well as the identity, which can be something like just Bob's name or email address or a website domain, as well as an expiration date. There are a couple other miscellaneous things that you can tack onto those, but those are the main things that we care about. The expiration date is so that if, say, Bob loses his private, say Bob's private key is compromised, it won't remain signed forever. It'll expire at some point. This still has the drawback of there being a single point of failure for security, because if the root certificate authority's keys are ever compromised, again, an adversary could just use that to sign certificates that people trust. But it does have the advantage that anyone can distribute keys as long as they have the attached certificate, so it scales better and it's no longer a single point of failure in terms of availability. And revocation, essentially if an entity's keys are compromised before the expiration date, then the CA will publish a list of certificates that have been revoked, which your device can query. That kind of has the same problems as the trusted directory, how in terms of availability, if the adversary can take down the revocation list, then you have the same problems, but it's just kind of what we've got. So does this all make sense? This is all review. Are there any questions on this? Okay, so let's get to the discussion sheet. I'll get it pulled up on my iPad again. Oops. Okay, what time is it? 2:20. I think we can probably. Um, I'll tell you what, we'll come back to question one just because I do like question two and three better, and then if we have extra time at the end, we can circle back to question one. They're not really sequential in any way, so we can jump around. Question two, I do like in particular because it's kind of similar to sometimes some formats that you'll see on the exam. It'll give you a scheme, or in this case, it'll give you 6 schemes and ask you to think about the security properties for each. So I think let's just spend a moment on part A. We're a smaller group, so I don't think we need breakout rooms. But let's just go through A. I'll give you maybe 3, 5 minutes to think about it. And you can talk with each other. I'm going to pause the recording so you won't be recorded if that's something you're worried about. But yeah, we'll start again in 3 to 5. Um, there we go. So you guys said everything but 1 and 2. So let's take a look at this. Why can't we decrypt 1?
Because it's a hash function, and hash functions are one way,
Exactly.
right?
This hash here is one way. O-N-E. And thus, even though this is encrypted under key K, which Bob knows, once you put it through the hash function, you can't get it back out the other way. How about number 2?
I think by the same logic, you can't find C2.
Okay, but what about from C1? Because essentially what this means is this ciphertext has 2 parts. We send both the encryption of M under K as well as the hash of the encryption of M under K.
Well, you can find C1, but you still can't find C2, right? Or
So maybe this is a bit of a notational thing. What this means is that this ciphertext has 2 parts, and I know it has 2 distinct different parts. This M is the same. So essentially what we're doing is we're both sending the encryption, and we're also sending a hash of this, which is that. So we're sending 2 things, but it's from the same message.
oh yeah.
Mm-hmm. So because Bob has this K and he knows the encryption algorithm, he can in fact decrypt number 2. Just take C1 and decrypt it. Does that make sense?
So as long as you can decrypt C1, it doesn't matter what C2 is.
Yeah, I think because this C equals C1, C2 essentially means that instead of just sending one thing, instead of just sending, like, for example, this hash up here of the encryption, we're sending both of these. So we're both calculating the encryption of M under K and sending that. And we're also, in addition to sending that, we're calculating the encryption of M under K and hashing that. So now instead of sending just, say, the encryption, we're sending both the encryption and the hash of the encryption.
Okay.
Mhm. So how about for number 3? We said we can decrypt it. And I'll just say yeah, because again, we have the same C1, which is the encryption of M under K. In fact, because we're sending it for 4 and 6, we know that for sure that 3, 4, and 6 are decryptable. How about number 5? You said we could, so how would we get back M from this?
Well, you can you can reverse the sign function by using the private key, I believe, or the
Mm,
secret key,
okay.
and then you can decrypt it using the symmetric key.
Okay. Do you remember how we hash things, how we sign things in RSA?
Um,
You have this E equals 3 and D equals your SK. If you remember, when at least in RSA, in order to generate some signature, so sign under SK of M, we actually take the hash of the message and then raise that to the power of our secret key, mod n. Does this ring a bell?
Kind of, yeah.
Right. So specifically for RSA, you wouldn't be able to reverse this sign function just because we hash it before we raise it to the power of our secret key. More generally, signatures generally don't allow you to reverse. Signatures generally don't allow you to get the message back as a whole. That's why you'd have to send both the message as well as the attached signature. That being said, signatures don't provide confidentiality. So if you ever have like a question of does this guarantee confidentiality, then you don't necessarily have that guarantee. But in this case, because this is wrapped in a signature algorithm, we say we cannot decrypt it to get back to the message. Does that make sense?
Yeah.
Okay. So the next question asks, which of the schemes that are decryptable in A also provide confidentiality? So we know we don't need to worry about 1. We don't need to worry about 5. So I'll pause the recording again. You guys can talk about it. So one of the good things I liked that you said is that we don't need to worry about C1 because it's always the encryption of M under K. And we assume Eves doesn't know K, so we don't really need to worry about any of these. So what we really have to worry about is can Eve learn something about the message through these things here? So we have to worry about these 4 functions here. So the first one, can Eve learn anything about the message from the hash of the encryption?
I don't think so. I mean, it doesn't. I don't think so. Yeah.
Right, because if you've essentially what we would do here is we know that the encryption doesn't leak anything, and thus when you hash it, you can't somehow get more information about the message.
Yeah.
So this one is confidential. How about for number 3?
Well, back to. I think it's confidential because the Mac doesn't leak anything.
Okay. Do you remember the correctness property for Macs?
Um, no, I don't.
Okay. So Macs are actually deterministic because essentially what if Alice and Bob are trying to communicate and Alice sends a message to Bob and she attaches a Mac, what Bob is going to do is he's going to try to calculate the Mac over the message and compare the 2 Macs and see if they're the same. If they're the same, then Bob knows that the message hasn't been tampered with. So does determinism pose a problem to confidentiality?
No.
It actually does. Because if we look at our NCPA game, um, if the encryption will always result in, or not even the encryption, if the function will always result in the same message, then the adversary could just ask for the encryption of M1, and then he challenges with M0, M1, and then if he gets back the encryption of, he knows the encryptions will be the same, so if he gets back the same encryption as before, then he knows that um, the challenger encrypted M1, else they know they encrypted M0. So does that make sense how that breaks in CPA?
Yeah.
Okay.
Yeah.
So in fact, Macs are not confidential. And it's similar to when I was talking about how signature schemes, while you can't recover the message, they're still not confidential. In the same way, Macs, while you can't really reverse it to get the message most of the time, it's still not confidential. So in this case, 3 would not provide security. So I guess that brings us to the final questions. How about number 4? The last 2. How about number 4 here?
Um, well, Eve knows encryption of KM, right? So Um,
Eve knows the encryption of KM, but we assume the encryption is in CPA secure. So that encryption is going to be probabilistic, if that's what you're thinking about.
oh, so C2 will change. Is not determined. C2 is not deterministic, so it should
Correct.
be confidential.
Right. And another way to think about it is similar to before. If this encryption doesn't give away anything about the message, then this hash can't give away anything about the message either, because you're just hashing that encryption. In the same way, macking the encryption of something should not give away any more information than the encryption itself. Of note, these two are using the same key. So the question does say that assume that the two keys don't interfere, using the same key doesn't interfere between algorithms, but usually you would use different keys. But because we're making the assumption that the algorithms work fine with the same key, this cannot give away any more information than the encryption itself. So that brings us to the last question. Number 6, is this in CPA secure, or is this confidential?
Um,
Yes,
yes.
Okay. Do you want to maybe try to justify why?
because we assume that the encryption is in CPA secure,
Mm-hmm.
so Eve shouldn't be able to decrypt C2.
Right. And essentially it's because even though the signature is deterministic in some schemes, even though the signature might give away information about the message, when we encrypt it, any of that information is now hidden. So Eve knows nothing about the message from C2. So that gives us 2, 4, and 6. And now we're going to do the same thing, except we have integrity. So I'll give you another couple minutes on this. So like before with this question, we can ignore 1 and 5 just because the question says we can. So I guess starting with number 2, does this provide integrity against Mallory?
No, because from C1, Mallory can calculate C2.
Right. Mallory could just say calculate some C prime, and then because hashing algorithms are public, she can just send C2 prime or C1 prime equals that, and then she'll just calculate C2 prime as C prime, as the hash of C prime. And now Bob doesn't have any way of knowing that this was forged. So 2 does not provide integrity. How about 3?
Yes, because that's the purpose of MAC.
Mm-hmm. Yeah, more or less. And likewise with number 4, we get authenticity from this MAC as well. These are actually 2 different schemes that people use in real life. This one, you MAC the entire message. You MAC the plain text and then send the MAC not encrypted. And here you MAC the ciphertext. In general, you always want to use this. You never want to do you always want to encrypt and then MAC the result of encryption. It's called encrypt then MAC. You never want to MAC then encrypt. And why that is a little bit out of scope. But it essentially relies on if you MAC and then encrypt, then you always have to try to decrypt something that hasn't been verified. And you'll see in the project, we tell you to always encrypt then MAC, never the other way around. But even still, both of these schemes do provide integrity for the purposes of this question. So 3 and 4 are good. How about number 6?
I'd say yes, because the signature cannot be reproduced by Mallory.
Right. And this is the third way of doing it. You sign and then encrypt the signature along with the plain text. So this does also provide integrity against Mallory because the signature, well, that's what the signature algorithm does. But again, you always want to, when working on the project, and if you ever write cryptographic related code in real life, you always want to MAC then encrypt. But all of these do provide integrity. So the last question we have is that many of these schemes are insecure against a replay attack. That's essentially if I've sent a message to Alice and say I've MAC'd it or something, then Mallory could just kind of take that message and send it again to Bob, and Bob has no way of knowing that I didn't send that message twice and instead someone replayed it. So I'll just pause the recording for a moment. You can talk about how you might want to defend against this, and then I'll start us up again. But yeah. So we were talking about how we know that these encryption algorithms are probabilistic. So if you encrypt something multiple times, you'll still end up with different ciphertexts each time. But the thing about that is that even if I send the same ciphertext to Bob twice, even though the ciphertexts are identical and they decrypt to the same message, Bob doesn't have any way of inherently knowing that that wasn't a replay attack. So that is getting very close to the answer. We also talked about signature algorithms and MACs, but those are also deterministic. So we would need something that includes some element of keeping track what we've seen before. So I think the answer that we were kind of circling around is that essentially what we can do is say I am Alice and I want to send the message, I don't know, because I'm uncreative. Essentially what we can do is we can define our message to be, say, the number 0 as well, and then, our actual message. And then we'll encrypt this whole thing under, whatever scheme we used. All of them always included us encrypting the message under K. And so what Bob can do is that when he receives this ciphertext C, and he decrypts it, he'll see that it starts with this number 0. And he'll keep track of, okay, I've already received the message with this, ID or this counter of 0. So now if Eve tries to replay that message to Bob, then he'll decrypt this and see that this is 0 again. So he knows that, oh, I've already received this message. Someone must have tried to do a replay attack. And can you see what Alice would do if she wanted to actually send this message again?
Just increment the ID.
Yeah. So then she'll choose her next message, say m prime to be 1, concatenated. Oh dear. Okay. 1 concatenated. This is the concatenation operator with her message again. I'm just going to get rid of this for the sake of readability. And then she's going to encrypt this as C prime equals the encryption under K of M prime. And then when Bob goes to decrypt this, he sees that, oh, now this is a 1. I haven't seen a message with 1 as the counter before, so I know that this is a new, fresh message from Alice. Does this scheme make sense?
Yes.
It doesn't have to be a counter. It could also just be some random number. But what this means Bob has to do is Bob has to keep track of what messages he's seen before. So Bob has to have some element of state, if that makes sense. Oh yes, the schemes providing both confidentiality and integrity are 4 and 6, and both of them include some. It's called a nonce because it's a number that we use once. So the modification is at a nonce. Does this all make sense?
Yeah.
Okay. We have 5 minutes left, so we don't quite have enough time to do either question. So I think, I think both of these questions are all right for you to do on your own, and then we'll release the discussion solutions on the website. But otherwise, we can just end 5 minutes early.
Okay.
I know this question took a long time, and I mentioned this earlier, but it wasn't being recorded. But a question like question 2 is something This is more in the style or like the theme of an exam question where they give you some sort of construction and you have to think about what the security guarantees are for it. And then maybe we would also ask you to think about how you would improve upon the scheme. So that's why I wanted to spend so much time on it, but I'm glad we did. So I will end the recording now since I don't think we have any more questions. But